Today we're going to talk just a little bit about kind of getting a little bit further into rational functions, and we've kind of worked with end behavior. A couple days ago, last class, we worked with, specifically how do those functions that approach infinity or negative infinity, what kind of an asymptote do they have in terms of the end behavior asymptote. Today we're going to kind of add in a couple new things and kind of combine a bunch of stuff together here. So first of all, what I'd like for you to do, once you're done watching this in class, what I'd like for you to do is just questions 1 and 2 only on that graphing rational functions worksheet. Tomorrow in class we'll probably go over those a little bit and kind of work on some of the other ones together on that worksheet. We'll also probably take a look at the project a little bit and kind of have some time to work on that in class as well. So let's just go ahead and take a look at this first example here. So hopefully the sub has passed this out to you. We're going to take a look just again at graphing rational functions when there's a little bit more going on. Now, the kind of interesting thing about this is we look at, let's take a look at this rational function. We have f of x is equal to x minus 1 over x minus 1. Okay, so take a minute to take your calculators out. And I'm going to start mine up over here. Of course, you can pause this whenever you want. Mine's kind of already set up to go here. I'm going to make a new document. And we'll just work on a graphs page here real quick. And what I'm going to do is just kind of type that function in here. So x minus 1 divided by x minus, oopsies, back to x minus 1. Make sure you wrap both of those in parentheses. And here's what we end up with, which is not a very interesting looking line. What we end up with there is a horizontal line. And there's a really good reason for that if you think about it, is that the numerator and the denominator in this case are just exactly the same. It's x minus 1 over x minus 1. So this entire function really reduces to the value of 1, which no matter what the value of x is, this thing always reduces to 1. Okay, now there are some interesting things to this, and I might need to slide this around just a little bit here to get this in view. Okay, so let's do this split screen thing. Again, we can do Control T to get to a table. And we'll notice that that function, again, for, I don't know if I can show that, for these values of x here, the function always reduces to 1. In the one case where that's not true, right here it says that it's undefined. When x is equal to 1, the value of the function is undefined. Now, that will not show up on the graph, unfortunately. If we kind of take a look at this, and maybe we'll hit Control T to get rid of this again, we don't actually see that there's not a point there. And in fact, as much as we want to try to zoom in on it, that's actually, we're never going to be able to see that. Zoom in here, see if I can get closer and closer and closer. I know where I am here, but what you're going to see is that I can go as far as I want to go, but the further I zoom in, I'm not actually going to see that there's a missing point there, because and really it's infinitesimally small, right? And so we already know what the graph of this thing looks like. Let's kind of look at the function itself and why that actually happens. So again, we'll go back to this and answer a couple of questions here. So what is the domain of that function? And certainly, hopefully you recall from last year that we do have some domain issues for rational functions, and really we have those issues when we have 0 in the denominator of a fraction, and that will be true for all of the functions that we're going to look at in this rational form. So when I look at question A, what is the domain of f of x? We'll just say, well, x minus 1 cannot equal to 0, and so x itself cannot equal 1. Okay? And so if we want to write that in interval notation, the domain of this is going to be from negative infinity to 1, not including 1, and then we're going to union that with the set from 1 to infinity. And so that's essentially again, that interval notation way of showing that it's everything, every single real number except for 1. Make sure you put parentheses there. If I put brackets there, that means it includes that value. So the parentheses just kind of jump right over that value. So what are the intercepts? The intercepts for f of x. So we kind of already know what the graph of that looks like. Basically, the idea is if kind of remember that back to algebra 2, that when I'm looking for intercepts here, and specifically I'm kind of thinking about what the x-intercepts might be. Okay, so whenever I have an x-intercept, that means that the y value is actually equal to 0. And so in any number, where I'm on the x-axis there, any place where that graph would cross the x-axis, that has a y value of 0. And so if I think about what that looks like in this function, I replace f of x with 0. Remember, those are my y values. And of course, x minus 1 divided by x minus 1 is never going to equal 0. We already know that it equals 1, so that is just a ridiculous statement. So for that reason, this one does not actually have an x-intercept. Okay, so this one has no x-intercept. I'm running out of space here. So let's try bringing this down here just a little bit. And so if I want to find my y-intercept, remember that the y-intercept can always be found for when the x value is equal to 0. Okay, so I can use the function here, my f of x, technically f of 0, I can plug that into the equation here. It's 0 minus 1 over 0 minus 1. Negative 1 divided by negative 1 is 1. And so my x-intercept really just becomes the point 0, 1. And we kind of already knew that, of course, from looking at the graph. We kind of cheated a little bit by looking at the graph, but I think conceptually it makes more sense to do that. So we don't have an x-intercept. We could plot our y-intercept here. Make that just a little bit smaller. We kind of know where that is. Okay. What is the end behavior in limit notation? So again, I might sort of jump down here towards the bottom here to give myself a little bit more space for this one. So end behavior notation, so remember our function here that we're looking at is x minus 1 over x minus 1. The degrees of the top and the bottom are the same. So this kind of gets back into some of the stuff that we did earlier. Both are first degree functions. And so to determine that end behavior, all I really need to do is to take that leading term from the top and take the leading term from the bottom. Again, since they're the same, it's going to approach some sort of a constant value. In this case, it's just the leading coefficients for x and x, which of course is just 1. So my end behavior then is going to look like this. The limit of the function as x approaches negative infinity is 1. And also the limit of the function as x approaches negative infinity would be positive 1 as well. And that's sort of confirmed by what the graph actually looks like. And then part D is we're just going to sketch a graph of what this thing actually looks like. So we kind of already know that. Now, the interesting thing that we have to sort of consider here for this one is kind of this domain restriction here. Okay. Now, what we know, we kind of know what the graph looks like. We have this horizontal line. But we also know that there's an issue when x is equal to 1, and that point is really, you can't really discern what that is by looking at the graph. You have to look at the function, figure out what is actually happening there with the denominators. And so the way we represent that on the graph is we put a little hole right there. And of course the hole is not really that big, but there's no other way to really show it. That we do actually have a horizontal line because this entire function just reduces to f of x is equal to 1, except at that single point when x is 1, the value of the function is actually undefined. And again, the reason for that is at this denominator, if I put 1 in there, I'm actually going to get 0 in the denominator, which kind of creates a problem. Okay, so what we have there, you can sort of look down underneath where the graph is. The graph appears to be a line at y equals 1. Of course, we have this. We have a hole in the graph. Okay, and again, that's coming from that domain restriction from the denominator. We have a hole in the graph. This is what's called a removable discontinuity. Okay, so we'll talk about a couple different kinds of discontinuities. This being one of them. It's just that the graph looks pretty much the same, exactly what it looks like. There's really nothing unusual about it. In fact, we can't even really see that discontinuity is there by looking at it in the calculator. We have to kind of dig a little bit deeper again with that, kind of thinking about the function there. So again, that discontinuity is called removable because the function could be made continuous if we just kind of put that point back in. There would be no jump there in the domain. Okay, we call that a removable, or we could take that one point away or remove it from the graph. It's a removable discontinuity. Okay, so let's take a look at the second example. Given this second function, h of x, this one's a little bit more complicated, so we have a little bit more work to do with this one. But either way, so we'll take a look. Given h of x is equal to function as given here. First of all, what is the domain? Okay, so what I would suggest for this, and we'll kind of get in the habit of doing this, is that this is essentially we have a quadratic divided by a quadratic. Some of the key features here that we're going to be interested in will come from the factors of the numerator and the denominator. The first one was pretty easy because x minus 1, we could solve that right away to figure out what the domain issues were there. Now this one, we're actually going to start by factoring this. So this numerator is going to factor to x plus 3 and x minus 2. Our denominator is going to be, what is that, x plus 3 and x, no, sorry, that's not right. There's no 3 in there. We're going to have x minus 2, I think, and x minus 1. That's better. Okay, those negative 2 and negative 1 give us that negative 3 in the middle. So there's our factorization. Okay, now the first thing we want to figure out here is what is the domain of that function. And again, the domain issues here are going to be what happens when the denominator of this thing is equal to 0. Okay, so what we're going to do is we're going to say, well, we don't want this thing to equal 0. So since we already have it factored, that's pretty easy to figure out. In this case, we could just say that x minus 2 would not equal 0, or x minus 1 could not equal 0. So x is not equal to 2, x is not equal to 1. Okay, so we have two domain issues here, one at 2 and the other one at 1. And so our domain for this guy is going to be from negative infinity all the way up to 2. All the way to 1, rather. We're going to union that with the numbers from 1 to 2, and we're going to union that with all of the numbers from 2 to infinity. So essentially we have all real numbers, but we're going to jump over 1, and then we're going to jump over 2, but everything else is still going to be there. Okay, so this part B says, what are the vertical asymptotes? So we kind of approached that the other day, no pun intended there, but we were looking at those ideas of vertical asymptotes with some of the stuff we were doing with the calculator the other day. And so I guess the idea here is that there will be quite a few times when these things have vertical asymptotes as well as these end behavior asymptotes. Okay, and so vertical asymptotes also come from domain issues. Okay, we have two different points here when x is equal to 2, when x is equal to 1, but they're actually two different things that are going on there with that. They're both domain restrictions, but they show up a little bit differently on the graph. And the reason for that is really that once we get this domain kind of figured out, we can go back and simplify this function. The x minus 2 cancels, and so what we're left with is this function right here. This whole thing really simplifies, and again, I'll kind of bring this down here. But this whole thing, h of x, actually simplifies to x plus 3 all over x minus 1. And the graph of that function that I have in blue there, the simplified function, is exactly equal to the one that we have initially in red, except for that one place at x equals 2. Okay, now this x minus 1 is going to be a little bit different. than what we had before. This one, notice in the previous example here that these x minus 1's actually canceled. So, I guess we're sort of looking maybe at going back to this. We had this f of x was x minus 1 over x minus 1, and we really just canceled those and just figured out that the function itself just reduces to 1. Okay, now that's true for every single value except when the x value is equal to 1. Okay, so remember we had a domain restriction, and that hole in the graph, or that removable discontinuity, came from the fact that we were canceling between the top and the bottom. Now that same thing is going to happen with this second example. Okay? We actually had something cancel here. We had the x minus 2 cancel. Okay? And so in this case here, that's going to create a hole in the graph. We'll kind of jump down to that just temporarily. So when x is equal to 2, because that's what we canceled. We removed that from the function itself by simplifying it. There will be a hole when x is equal to 2. That is one of our domain restrictions. The other one that does not simplify out of it becomes a vertical asymptote. So anything that still remains as part of the simplified function, in this case just the x minus 1 term, that's actually going to give us a vertical asymptote. Okay, so here we look at, well, x minus 1 is equal to 0, and so I don't want it to be equal to 0, and so x cannot be equal to 1. And so there is an equation, a vertical asymptote at x equals 1. Okay, now the way that's going to show up on the graph, we'll put that as we start here, kind of do these things in order. There will be a vertical asymptote at x equals 1. Kind of like when we were looking at tangent functions and things like that, we have vertical asymptotes here as well. Okay, now since we're sort of on the topic here of these discontinuities, let's just kind of think a little bit about part E. Part E says find the coordinates for any holes in the graph. Okay, so we already know what the x coordinate is. The x-coordinate of that, the hole in the graph, is going to be at 2, but we don't know exactly what the y-coordinate is going to be. Something is going to be happening there. There's going to be a hole when x is equal to 2, but where is that hole going to be positioned vertically with the y-coordinate? And so the easiest thing to do with that is really just to kind of go back down to this equation at the bottom. Let's do this in red. Use the simplified function. If we try to use the non-simplified function, we're going to get 0 in the denominator. It's not going to do us any good. So we'll take the simplified function and just plug that in. So instead of having x plus 3, we are simply going to have 2 plus 3 and then 2 minus 1 in the denominator. And what that reduces to for us is just 5 over 1 or 5. That's the y-coordinate, right? That's the value of the function when x is equal to 2. So, the coordinate point for that hole is going to be at 2, 5. Again, just putting it back in that simplified function. Pretty straightforward. Okay, so what that tells us, we go back up here to the graph, we can put that in here. When x is 2, y-coordinate is 5. At that location of 2, 5. So the graph is going to go around that point, not literally around it, but it's going to go kind of through that point, but that point's not going to be there. Okay, well, hold on, might make a little bit more sense here in a couple minutes. Okay, so that's the coordinate points for the holes, or just one hole in this case. We do have vertical asymptotes. We kind of got our domain stuff out of the way. I guess we can kind of look at what the intercepts are going to be for this one. Again, we're just trying to get enough information on the graph to give us a picture of what this thing is going to look like. And the goal of all this is to try to put some of these pieces together to come up with what the function actually looks like without having to use our calculators. And again, this will be a pretty important skill in calculus next year, these ideas of asymptotes and rational functions and domain restrictions and all that. Pretty heavy idea in calculus. And again, we don't have to do this in any particular order. I think maybe we can do C here, I guess. And I'll probably come down here, but we're trying to find the x, or just the intercepts in general, right? So if we're trying to find the y-intercept first, remember that happens when x is equal to 0. And so what we're going to have for that is, quite literally just really plug in x equals 0 in for this guy. And so, again, we can work, once we kind of get that, the function simplified, we can just use the simplified function. The only place where what I have the simplified function is not going to represent the original function is at this one domain place right here when x is equal to 1. Otherwise, they're exactly the same. So we'll kind of cut down on the amount of work that we have to do for this. And that will make things a little bit easier for us. So we're going to use this, we're going to continue to use this simplified function here. So when x is equal to 0, we're just finding h of 0. So we plug 0 in for x here, 0 in for x in the denominator, and this ends up being -3. So what that tells us is that we have a y-intercept of 0, -3, which we can plot here. Trying to find the x-intercept or intercepts, we do kind of the same thing, x-intercept, except for y is going to be equal to 0. And so here, we're trying to figure out what the y value is. I'm just going to, instead of h of x, I'm just going to put y there. Actually, I'm not going to do that because y is equal to 0, so the value of the function itself is 0. And x's kind of stay the same. That's what we're actually trying to solve for. So again, taking the original function, we're just going to put 0 in place of y, or h of x, and then we're going to simplify that. Okay. Now, the interesting thing about this is that, really what happens here, and we kind of think about maybe, multiplying by this on both sides if we wanted to. Mathematically, it's kind of an odd thing to do. We end up with this, and so in this particular case, x is going to be equal to -3 when y is equal to 0. And so one of the shortcuts that you can use for this is that the only way that a fraction, the value of fraction, will ever equal 0 is if the numerator itself is equal to 0. Okay, so we can always, if we want to, we could just look at what the numerator is and kind of disregard what's in the denominator. The only time we're going to get 0 through division is if I have 0 divided by anything. It doesn't matter what this thing down here is, as long as it isn't 0. If I have 0 in the numerator, then the whole value of the fraction is equal to 0. So, we can set this equation up a couple different ways. Either way, we end up with this this kind of reality here that x is equal to -3. That gives us our x-intercept. So, we also have one at -3, 0. So, this one here. Okay. Not bad so far. Okay, so part D, what is the end behavior in limit notation? So again, I'll probably need a little more space here. I'm probably going to bring this one down. Okay. So end behavior. So again, this goes back to what we've kind of been working on here. We have pretty much, it's not f, we pretty much have h of x simplified to x plus 3 all over x minus 1. And so again, so we have a first degree function on top and a first degree function on the bottom. We're going to end up with a non-zero finite asymptote here. So we have here, we just again take these leading terms out of here. X divided by x is equal to 1. And so that's our end behavior for this one. So if we were to write this in limit notation, kind of similar to what we had for the last one, the limit of the function as x approaches infinity is 1, and also limit of the function as x approaches is negative infinity, is equal to 1. So this will be the answer for that part. Okay, now what that tells us, when we have a non-zero horizontal asymptote, or non-zero end behavior, is that this equation at y equals positive 1. That's going to be a horizontal asymptote. That's also how our end behavior is going to work here. All right. So we really kind of have everything that we need to piece this problem together. And so what we kind of have to have a sense of, and we'll get a better sense of this as we do more problems like this. So we kind of get a sense of how these graphs work. The idea is that these asymptotes generally provide, kind of like they did, we were doing trig stuff with tangents and cotangents and some of those other things. They provide a framework or a structure for the graph. We've kind of seen the way a couple of these things will look. And so this one, just kind of having a little bit of intuition, which we'll get better at as we continue with this. The graph of this thing has to go through these 2 points. Okay? And then it will kind of take off and follow this vertical asymptote down. And then on the other side, the same kind of thing is going to happen. I'm going to have a point up here. I know again that hole, that the graph is going to go kind of through that hole. So that gives me a sense of where the graph is there. And it's just going to pick up on the other side, and then it will approach this asymptote as it goes out to the positive infinity direction. Okay, so this is pretty much what the graph is going to look like for this one. And again, if we wanted to, let's go ahead and do this real quick. We could actually see if I can clear this mess out of here. And we could look at this graph as a whole here. So we'll do this division. So this will be x squared plus x minus 6 on top. We're going to divide that by this one, which is x squared minus 3x plus 2. There it is, sorry. Okay, and we can kind of see that that's pretty much what we had before, and we'll see, maybe I can get this to right on the board here, but we'll see that our important things here, that our our x-intercept was -3, our y-intercept was -3. Okay, we have this vertical asymptote here, and then we also have this horizontal asymptote, which is about at 1. So that kind of confirms what we had before. And then also, if we do a split screen on this, we can do Control-T. And notice that our 2 domain issues here, which I just kind of wrote over here. Hold on a second. Oh, jeez. Get rid of that, get rid of this. Our domain restrictions here are at x equals 1 and 2. And we can see, you can drag this over, this is undefined. It's also undefined at 2. Now again, that shows up in 2 different ways. The one, because 1 was not able to be simplified out of there, that still remained in the denominator. This is going to be a vertical asymptote. And our location at 2 is undefined here also. Now again, that shows up a little bit different. We can kind of look over here and see that it's not as obvious as that there's an issue here. The vertical asymptote, really clear what's going on there. Here, if we have x equals 2, it actually kind of looks like there's a point there. Okay, it's not. We kind of know that it's not, but by looking at the graph on the calculator, you're not really going to know that there's actually just a small hole in that graph at that one specific point, 2,5. Okay, so I think that's probably where we're going to cut it here for this one. I think, so what I'll have you do is, once you're done taking a look at these, what I would like for you to do is to get into groups and to kind of work on just the first 2 questions from that worksheet. We'll come back tomorrow and we'll do some more of these things together. We'll kind of go over maybe the homework questions that you're working on right now. We'll also look at the project a little bit. But I think that's pretty much it. So thanks for listening, and mark any questions that you have, and I'll try to clear them up best I can tomorrow. Again, maybe, sorry, I'm going to just put this on here again. So your homework here, graphing rational functions, worksheet 1 and 2. I'm just going to put those on the back of the worksheet. So Go ahead and get started on those.